Good. So now on to something completely different. Well, not completely different. So we started to talk about volume visualization last time. What it is, where the volume data comes from, how it's laid out in 3D space usually, and the challenges associated with volume visualization. And then we looked at an amazing demo video, which I've uploaded to YouTube. Thank you very much. Everybody sign on the attendance register. Just put the data on.
It's on the top left.
So the volume data is usually laid out on either as a set of cells or so-called voxels. Anybody ever heard the term voxel before? Another good answer would be, oh, I previewed the lecture from the last time you taught it off. So everybody knows, so voxel is a short term for volume element, and it comes from pixel, which is a short form of the picture element, and that's something, so it's the 3D equivalent of a pixel, and it looks like this, right? The data is stored at the center of a cube, typically, and then we have our 1, 2, 3, 4, 5, 6 neighbors, our 6 face neighbors, so to speak, in the 6 face neighbor cubes. And then we can interpret the same data by shifting this grid. If I just shift this grid 1/2 unit to the right or left, it doesn't matter, and then another ½ unit down or up, it doesn't matter, we get the data is stored at the corners of cells. Right, so they're basically the same, it's just that the grid has been shifted 1/2 unit in 3 directions, X, Y, and Z. Right? And here we're always interpolating the data along the edges and inside the cells to get values, to obtain values for our algorithms. Has anybody ever heard of that word interpolate before? I noticed interpolation and extrapolation are used kind of often in Hollywood. Has anybody noticed that? I was watching a TV show just the other day and I noticed, oh, can't you extrapolate the data? Or can't you, actually what the character should have said was, can't you interpolate the data? They got it confused. But anyways, I just noticed that these terms are used in Hollywood. Not that seldom.
We use the graphics setting here.
Interpolation?
Interpolation, that sort of stuff.
Do you remember what it means?
I was an algorithm to convert 3D to 2D. I think that point.
So you like derive a value from between two.
Exactly. What's your name?
Khalil,
exactly. So deriving a unknown value from 2 previously existing. If the unknown is between the 2 previously existing one or more than 2 previously existing, then it's called interpolation. If it's beyond the range of the existing values, then it's called extrapolation. And we're going to talk a lot about interpolation in this part of the, well, a lot. We're going to mention this a lot in the next lectures and for the rest of the module. So if we look up interpolate in the dictionary, it says estimate a value of a function at a point P given a known function values and points that bracket P. So before I just try to explain this example, one kind of application is the weather, right? So if I said, oh, what's the temperature in Bridge End? How does the Weather Channel or the Met Office know what the temperature is in Bridge End? They do know, right? Because you can look up, like Google, temperature in Bridge End, and there's a value there. But how do they know that there is what the temperature is in Bridge End?
Either they have a sensor or they have two sensors nearby.
A weather station in Bridge End. So there's one possibility. You have a weather station in Bridge End that's measuring the temperature. But can you have weather stations everywhere? Can you have them everywhere? No. We could use one in this room. I'll just bring a thermometer for this room. But you cannot place weather stations everywhere, right? It's too expensive. But you want to know the temperature everywhere. What could happen is, what's more likely is there's a weather station in Swansea, which I think is at the top of Kilvey, the Kilvey Hill. By the way, anybody ever go up there? There's a huge station, like tower, with all these devices and antennae and satellite dishes, but I'm sure there's a weather station up there. And there's going to be another one in Cardiff. So we can derive the temperature in Bridge End based on the temperatures of Swansea and Cardiff, right? And for all the towns in between, all the beautiful of South Wales, in between Swansea and Cardiff, based on this weather stations in Swansea and Cardiff. And we can do that using interpolation. And there are different ways to interpolate. Right? Imagine we have an unknown value p, right? And we have a known value at f1 and another known value at f2. Well, one way to derive the temperature at p is one way is just the simplest way is called nearest neighbor interpolation. So we find our nearest neighbor, in this case it's f1, and we just take that value or use the same value. So Bridge End is might be a little bit closer to Swansea, and therefore we would take the Swansea value. Another way of interpolating is using both values and then a formula, right? This formula, this is the linear interpolation of P. It takes into account the distance that P is from the first one, and the distance between P and the second sample, and it computes a weighted average. Has anybody heard that term before, weighted average? Yeah? Everybody knows what an average is, how to compute the average of some numbers. Anybody want to explain how to compute the average of some numbers? Fabio Simmons is here somewhere, at least he signed. Fabio, how do you compute the average of some numbers?
Isn't it a sum divided by how many samples you have?
That's right. You add up all the numbers and then you divide by the number of them. That's an average. So in other words, the weight of all the numbers is the same. They're given all the same importance or the same influence. They're all treated equally. But in the weighted average, they are not given all the same importance. Some are more important or have a heavier weight than others or are more influential. So that's what these two terms are. These are weights. So they compute a weighted average because we have these weighted terms, right? When D gets really small, the the weight of F2 becomes very big. And when this D gets very large, the weight of F2 gets very small, right? Because D is in the denominator. And here's just a little example. Right, imagine I actually plug in some numbers. There's our original. And now I'm plugging in some numbers. I want to compute the temperature here. Right, and I have a temperature here, and I have a temperature here. You can imagine Swansea and Cardiff, for example. This is where that analogy starts working. If I have a temperature of 100 degrees in Swansea, and then 200 degrees in Cardiff, and I want to, well, if I use nearest neighbor interpolation, and I'm only a distance of 2 away from Swansea, then I just take the value at Swansea, 100 degrees Celsius.
Were those Fahrenheit originally?
Say it again?
Were those Fahrenheit originally?
Were those what?
The temperature, were they in Fahrenheit?
I was just trying to use some numbers that are easy to see. Like, if I want to compute a weighted average, look, this unknown value is much closer to the left point. So the left point has a greater influence, right? So it's actually 80% the way towards the left point. So this gets turned into 80%, this weight factor. That's 80% of the influence. So 80% of the temperature at the left plus 20% of the temperature at the right ends up being, right, 80%, 20%, add them together, you get 120 degrees Celsius. So that's an example of linear interpolation. Does everybody follow that? If that term confuses you, and some people it does confuse, you can think of the phrase weighted average. So mathematicians and computer scientists and computer graphics people have invented a lot of terminology, and some of the terminology is fancy and can be reduced to something simpler. This is what the formula for linear interpolation looks like in 3D. Right? That was a linear between 2 points, but if we want to interpolate between 8 points in 3 dimensions, the formula looks like that, and that you'll have to memorize that, and that'll be on the test definitely. Now, you won't have to memorize that. I couldn't memorize that either, but I know how it works. So the three-dimensional trilinear interpolation, it's called, one way to implement that is to do four linear interpolations along x. So 1, 2, 3, 4. So then you have 4 points, and then you do 3 interpolations along, 2 along y, right? 2 there, and then 2 there. And then 1 more along z, right? So you have 7 altogether. You have 4 plus 2 plus 1. So 1, 2, 3, 4, and then 5, 6, and then 7. It's hard to see. I'm just waving my hands around, but that's how it works. The nearest neighbor interpolation just looks at the distance, checks the distance to the 8 vertices at the cell corners, and uses the value at the nearest one. And these choices of which kind of interpolations to use have consequences. Right, if we try to render a sphere using nearest neighbor interpolation, you can see that there are artifacts. Right, you can see something that looks like pixels. Even here, it looks much smoother. Actually, if you look very closely here, there are still artifacts, so it's not perfect. Anybody know what those artifacts are called? Those kind of staircase artifacts that pop up? Those, anybody, you took computer graphics? What's your name?
Ben.
Ben. Is it aliasing? Yes, exactly. That's called aliasing artifact. Correct. So that's some terminology. We're going to be using those terms a lot, so it's good to understand what they are. Now, to kick off the Volviz algorithm space, or the topic in more depth, we're going to go through this conceptual Volviz framework. By the way, we did this twice already. We did something like this twice already. Anybody remember? Does this remind anybody of anything? We had this thing called the ubiquitous pattern of learning. And then we had another diagram like this. Anybody remember? It was called the Viz pipeline. So we had two kind of frameworks, or two conceptual frameworks prior to this. And this is like a piece. This is like the volume visualization Viz pipeline piece. It's like the Viz pipeline for volume visualization only. So in this framework, it has two starting points instead of just one. We start with the sample data or the measured data. That's from a machine, right? And then we can store that as a set of voxels and call it voxel space. And from there, we can extract surfaces. Remember, voxels are cubes. We can extract surfaces and represent something in geometric space, right, as a set of triangles. And then we can perform a surface rendering. Or we can go directly from voxel space to pixel space, right, which is also rendering. So like here is another line. Above this line is three dimensions, and below this line is 2 dimensions. That line or that transition was also in the Viz pipeline, a 3D to 2D transition. But now we have two different options for 3D to 2D rendering, 3D to 2D rendering transition. Another possibility is to start with analytical data. Then we generate a geometric surface, and we render the surface to 2D space. We can also convert geometric data or surfaces to voxels. It's possible. It's not very common, but it's possible. So we can traverse that volume visualization framework in all those different ways. And if any, question?
We were thinking about getting 3D into 2D. What about opposites?
What about what?
Opposites. So getting 2D data and putting this into 3D. So creating from pixels, create voxels, and from voxels, create the 3D mesh model.
Are you on drugs?
Why?
Nobody's ever asked that question before. It's a very good question. It's really good. It's a very advanced question. So if everybody heard, what about going backwards from 2D to 3D? That is very possible, and I would say it's an area of research. It's an unsolved problem. There are many solutions, but I wouldn't say that it's classified as a completely solved problem. But there are lots of ways to do that, to go from 2D to 3D.
So it is possible?
It is possible, definitely, definitely. And it's like an example, you can Google lots of examples, but one like hot topic, at least, I'm not a computer graphics person, so I'm getting a little outside my comfort zone because what you have is a little bit of, in some ways, a computer graphics question. But what it's called is reconstruction. So how do we reconstruct the 3D space from the 2D, from a set of 2D data samples? And there are several different ways to do that, and there are several different applications. But like one of the fun applications and one of the fun directions of research is reconstructing cities. So that you can Google that, and maybe we should. Maybe we should Google that right now, because that's such an interesting question. Reconstructing cities from photographs. Has anybody ever looked into that? I guess I spelled it wrong. But so reconstructing, well, the most famous one is probably Rome, right? And if I just click on images, I wonder what happens. But there are millions and millions and millions of photographs of Rome, right? From tourists. And they upload them to places like, what are those websites that take all your photos? There's lots of them. But Facebook is one of them. Instagram is another. But there was Flickr was another one, very, very popular for a while. You can take those photographs and reconstruct cities from those photographs and create a 3D model. So that's a very active research direction. But there's another active research direction is trying to reconstruct a 3D volume from X-ray images, which are 2D. So imagine placing an object in the center of a coordinate space, and then you have an X-ray camera. You take a snapshot. X-rays are inherently 2D, a 2D projection. Then you rotate the configuration by 1 degree. You take another 2D image, and you rotate the whole thing around by 360 degrees. You're left with a series of, say, 100 or 1,000 or maybe more 2D projections, X-ray projections. And then the question is, can you reconstruct those to form the original 3D object? And the answer is yes, you can. Okay. The open questions are, how accurate can you do it? And how quickly can you do it? These processes are typically very slow. Yeah. So those are just two examples about going backwards, so to speak. We won't really talk that much about that in this module, actually, because it's beyond the scope of that module. It's a very good question. That's why I asked if you were on drugs. And I'm sure there are other examples that I'm not thinking of, because I wasn't, thinking about that question. But I do remember the first time I saw a talk from a computer graphics researcher that was actually writing a program to reconstruct cities from photographs. And I was blown away. I thought, that's amazing, like reconstructing a whole city from a set of photographs. And he showed like the city, a 3D version, a model of Rome or something, and you could fly around and you could look from at the street level, at the sides of buildings and stuff, and I just thought, that's amazing. So there's some really impressive work going on in that area. Those are very different, well, they're different applications and they're very different in their approaches and so on, but they're nonetheless very interesting. So technically there should be an arrow going back up, and even maybe one going back up, there too. But we won't have that on the test. So here's an example of traversing the conceptual volume, this framework, starting with CT data, measured data on the left, right? Computing a grid, equally spaced grid where the samples are all uniformly spaced in in 3 dimensions, right? Compute deriving a voxel space, the data enhancement. That's, by the way, that's data enhancement in the Viz pipeline, if you can remember the Viz pipeline. And then rendering it using either volume rendering or surface rendering. In this case, somebody has decided to compute isosurfaces. The user, we haven't discussed what those are yet, and then render those surfaces to 2D space. Right? There's a surface representing the skin here, there's a surface representing the bones, and there's a surface representing soft tissue. And to me, it looks like there are 3 surfaces there. Or maybe there's 4. There's like a reddish surface, maybe 2 soft tissue surfaces. It's hard to see. It would be easy to see, by the way. I would be able to easily see if I could rotate the scene. So in 3D, the idea of rotating is very important. Very important. Here's another example. Instead of creating surfaces, the user in this case has gone straight down the left, right? Started with the sample data, represented it in voxel space, and then done something called volume rendering or direct volume, maximum intensity projection, which we haven't talked about yet, but that's what this is. And then they've rendered this image, which are vessels in hand. We're going to explain all these in more detail. Here's the example on the right side. Somebody starting with an analytical data set for modeling. So that's a data set that's described by an equation, for an example. You input a 3D coordinate, like x, y, and z, and then the equation gives you a scalar value in return, or a vector value in return. That's analytical data. And the user has decided to extract surfaces, analytic surfaces from the analytic data, and then render those surfaces as a set of triangles. Right? And here's an example. And it's not the world's best example because you can see it's got some aliasing artifacts, but you get the idea. This is a very common source of analytical data comes from mathematics. Right? Mathematicians describe their surfaces analytically. So that's the conceptual volume Viz framework. And that's like, imagine a focus and context visualization of the Viz pipeline. Where you start with the Viz pipeline that we described, and then you zoom in on the vol-Viz part of the Viz pipeline. That's what you would see. Okay, so we're going to talk a little bit, these are the next kind of topics in the vol-Viz section. We're going to talk about slicing, so-called surface fitting methods, like how to extract those surfaces from 3D volume data. And then we're going to cover something called direct volume visualization. There's no conversion process of the sampled data to surfaces. It's taking that data and projecting it directly to the 2D space without conversions in any way. But the technique that's used in that case is called direct volume visualization. And there are different kinds of direct volume visualizations that we're going to talk about. I guess we're out of time-ish. Are there any questions about something volume visualization? Exciting things? Okay, good. Happy Monday.
Since I'm on tracks, okay? Since I'm on tracks.
Yeah, you're on tracks.
Yeah.